People talk about the four main categories of biomolecules: sugars, nucleic acids, peptides and proteins, and lipids. Lipids are probably simpler than carbohydrates, nucleic acids, and peptides and proteins, but that doesn't mean they're not important. They're extremely important to everyone. There's a spectrum of lipid molecules, and to a newcomer, this can seem overwhelming. So let me do what I've done before with sugars. I said, with sugars, concentrate on learning 3 monosaccharides. They were glyceraldehyde, D-ribose, and D-glucose. If you do that, that's a gateway to lots of different biological chemistry. With the lipids, let's talk about 4 types. There are others. People will say this is too simplistic, but 4 types covers a whole lot that's relevant to biomedical sciences. The first of those 4 types is triglycerides. If a patient goes to a doctor and asks for a test to check on their heart health, a lipid panel is maybe what the doctor will order. And that encompasses triglycerides, and they should be in a certain level. If they're not, you have too much fat circulating in your bloodstream. Whenever you have this type of blood test done, you should fast overnight beforehand, because the amount of fat in your bloodstream depends critically on what you've eaten before. Triglycerides are actually just triesters. They're triesters of glycerol. That's a 3-carbon molecule with 3 OH groups. It's convenient to draw glycerol on its side and project long alkyl chains which form when 3 esters are made from 3 fatty acids. What are fatty acids? Well, they're aliphatic compounds that contain typically no double bonds or cis double bonds, and occasionally trans double bonds. So you might imagine that triglycerides are very hydrophobic molecules, and indeed, that's true. The process of taking glycerol and forming 3 esters out of it is esterification, and the process of taking the triglycerides and hydrolyzing them back to glycerol is hydrolysis or saponification. Fatty acids used to make triglycerides can be all the same. They can be 2 the same and 1 different, or they can be all different. Interestingly, most fatty acids have an even number of carbons in the chain. The reason derives from the metabolic pathways by which they're assembled. And that becomes very important later on in considerations of metabolism. So far, I've shown triglycerides from aliphatic fatty acids, but these fatty acids contain alkenes sometimes. They can have 1 alkene or several in the chain. If all the fatty acids are saturated, no double bonds, then we have a saturated triglyceride. So triglycerides are fats. If all the chains are saturated, that gives you a saturated fat, and that tends to be higher melting point. Think of coconut oil and butter, melting point approximately room temperature. If we introduce double bonds into the chains, then the chains must kink. They can't pack together as nicely. So unsaturated triglycerides have a lower melting point because they don't pack together very well. That makes olive oil a liquid at room temperature. In this video, I explained how trans fats can result from hydrogenation of cis fats in processing vegetable oils. Why would food manufacturers hydrogenate unsaturated vegetable oil. If the unsaturation in a triglyceride can be hydrogenated away, then the resulting processed oil will be more stable. It will have a greater shelf life. It can be manufactured and stored more easily. The danger comes with partially hydrogenated oils. So even starting with cis fats, partial hydrogenation will cause isomerization, giving trans fats. And a classic one is margarine. If you eat cakes and biscuits and cookies, shortening pastries, typically these have trans fats in them. Recall that if we take a triglyceride and hydrolyze the three esters, we form fatty acids, and they are a form of soaps. This is the process of saponification. So why are triglycerides possibly the most important category of lipids? It's because they're central to metabolism. Fats store a lot of energy, and they can be oxidized in the mitochondria to give ATP. And of course, ATP is the fuel on which cells operate. But no cell could operate without a cell membrane. Phospholipids are like triglycerides. They tend to be based on glycerol, but they have two fatty acids and some other polar group on the third oxygen. In a cell membrane, those polar groups present to the exterior of the cell, and they present to the interior of the cell, and the fatty acid chains packed together in between, in the transmembrane region. And this provides a really useful anchor for proteins, peptides, and oligosaccharides. Besides phospholipids, there are other molecules with aliphatic side chains and polar head groups that embed in the membrane, and they are lipids also. In summary then, phospholipids contain glycerol. Two of those sites are taken up by fatty acids. The third one is a phosphate group. I'm sure you've all heard of the third category that I'll talk about here, and that is the steroids. Steroids have amazingly potent biological activities. Those of you who take contraceptive pills will know that that tiny pill has a dramatic effect on your body. Steroids have 3 6-membered rings joined in a particular orientation, and they must have 1 5-membered ring. They have the same framework, and onto that framework is added functional group. I hope you remember the structure of decalin. Decalin is 2 6-membered rings fused together on one edge. A decalin framework underpins the bottom of the steroid, as I've drawn it here, for the sex hormones, estrogen and testosterone. And you'll note that in those sex hormones, the 6-membered ring at the end of the molecule can be unsaturated. It can be aromatic, it can be an enone, for instance, as in progesterone. But other steroids may be totally saturated in that ring, and that means we can have trans-decalin orientations at that AB ring, basically this shape, or cis orientations at the AB ring, this shape. But the stereochemistry at the other ring junctions doesn't change. So steroids are predominantly flat, rigid molecules, maybe with some turns at the end for a cis-decalin containing one, or the 5-membered ring, of course, is flipping between envelope conformations. Interestingly, cholesterol in a cell membrane makes it more rigid. And rigidity in a cell membrane can be desirable, as in a lipid raft. It can also be undesirable, as in calcification of an artery in heart disease. The fourth category of lipids that I like to talk about are waxes. Waxes, of course, you can burn in candles. Beeswax, used by bees to make hives. Amazingly, in perfect six-membered rings, back to back, like the structure of graphite. Waxes are simply long-chain fatty acids in an ester with a long-chain alcohol. I have a chapter on lipids in my workbook. It covers quite a lot of ground. You can see that summarized in this flowchart here. Thank you very much for listening. Bye-bye. Et forma me secundum voluntatem tua